Hello everyone, I am Professor Anis Vora and I welcome you all in this video lecture. In this video lecture, we will study about one of the application of Zener Diode as a voltage regulator. First of all, let us understand the need of voltage regulator. Why we require voltage regulator? The DC load voltage across the load change in two conditions. The first condition, the change in AC voltage applied to rectifier. As an input of rectifier, we use AC voltage, and if AC voltage change, either increase or decrease, then accordingly output of rectifier, that is DC voltage, that also change, either increase or decrease. And the second condition, that is change in load condition. If load current increase or decrease, accordingly output to load voltage might increase or decrease. So function of voltage regulator. The function of voltage regulator is to maintain the DC output voltage constant across the load in any condition, and we can use Zener Diode as a voltage regulator. For example, if we see the output voltage with respect to load current, if our output DC voltage is regulated, then it remain constant. Here it is 10 volt. In any load condition, it remain constant. But if it is unregulated, then with load current, output voltage might change. It might decrease. So now here the function of voltage regulator comes into picture. To maintain the output voltage DC constant, and that is known as a regulated, we use a voltage regulator. Now let us see the block diagram. We have mains input, that is our AC supply. We use a power transformer to step up or step down the AC voltage, and we get our required DC voltage accordingly. Then we use a rectifier. Rectifier, we know that AC voltage can be converted into DC voltage. The next block, that is a filter circuit. Output of rectifier, we know that we get a DC voltage, but it is a pulsating in nature. So to make it smooth, we use filter circuits. We have different types of filter circuits. And then now to make the output voltage constant, we use a voltage regulator after a filter circuit. And then we connect the load. So this is entire block diagram to understand the rectification, filtration, and then a regulation. Now let us see the waveforms. We have input AC voltage. We know that it is a sinusoidal. With the help of power transformer, we can step up or we can step down. And then the output of rectifier. We know that it is a pulsating in nature, but it is a unidirectional, and we can call it DC voltage. Once this DC voltage we apply to filter circuit, then we have smooth DC output voltage. The smoothness of output DC voltage depends again the type of filter circuit we use. Then when we use a voltage regulator, the output voltage remain constant throughout any load condition or line condition. Load condition is a load current change. Line that is our input AC supply, voltage at the AC side increase or decrease. We can have a regulation on both the side, load side as well as on the line side. In both the condition, output voltage remain constant. So this is function of voltage regulator, and to maintain the output DC voltage constant, we use a voltage regulator. We are using Zener Diode as a voltage regulator. So let us study the voltage and current, that is VI characteristic of the Zener Diode. We have forward voltage, we have reverse voltage, forward current as well as reverse current. In forward biased condition, the characteristic of Zener Diode, that is similar to the PN junction diode. We have knee voltage, and once the forward voltage cross the knee voltage, then we have sudden rise in the forward current, and then voltage drop across the diode remain constant around 0.7 volt or 0.4 volt, depends on the germanium or silicon diode we use. But this condition is easily available in PN junction diode, so we do not use Zener Diode in this condition. We always use Zener Diode in reversed bias condition. So when we apply reverse voltage to the Zener Diode, up to certain voltage there is only a very small leakage current flows, but at certain voltage, that is known as a Zener breakdown voltage, Zener breakdown happen, and at a certain Zener voltage, current start increasing and output voltage across the Zener remain constant. This Zener breakdown can be planned according to doping level we adjust during manufacturing. So Zener voltage, various Zener voltage is available, and we can have exactly the output voltage as per our requirement. We have minimum Zener current in a reversed bias condition. Then we have maximum Zener current, and between maximum current and minimum current, that is known as a Zener breakdown region. Constant voltage is possible between these two current limit, and this is known as the Zener breakdown region. Zener voltage remain constant for these two extreme condition of current, minimum as well as maximum. So this characteristic of Zener diode, Zener voltage and Zener breakdown region we use as a voltage regulator. Now let us see the block diagram. We have a rectifier and a filter, and we have a load. Between rectifier and filter, and when we connect output to the load, in between we have a voltage regulator. So output of a filter circuit, that is a VI, that is a input voltage to the voltage regulator, and output of the voltage regulator across the load, that is a VO, that is output voltage. The function of voltage regulator is to maintain this output voltage constant irrespective to any value at the input side, and that is a VI. So here we use a Zener diode across the load in reversed biased mode. So anode is connected at the negative side and cathode is connected to the positive side. So in this block diagram we can easily understand how we can apply Zener diode as a voltage regulator. Let us elaborate our circuit in detail. So we have input voltage to the voltage regulator, that is the VI, that is output of the rectifier and filter circuit. We have positive as well as negative terminal. We use a series resistance, that is RSE, in series with the load resistance, that is RL. We use a Zener diode across the load. Total current passes through the series resistance, that is ISE. After that, the current is divided into two parts. The major part goes to the load side, that is IL, that is a load current, and some part goes to the Zener diode. Once the voltage exceeds the Zener breakdown voltage, then IZ, current IZ passes through the Zener diode. And output voltage, that is a VO, that is across the load, and that will be maintained constant by the Zener diode. Now let us see the working of the Zener diode as a voltage regulator. Zener diode adjusts its current such that its voltage remain constant irrespective of the changes in the input voltage or in the load current. In both the condition, output across the Zener diode are maintained constant. ISE, that is a current passes through the series resistance, and that is IL, that is load current, plus IZ, that is Zener current. Now let us see the equation for output voltage. Output voltage, that is VO, that is output voltage. Now we have VI, that is our input voltage, and mathematically it is exactly equal to the VO plus the voltage drop across series resistance, that is the product ISE and RSE. So to maintain the output voltage constant, we have to adjust the voltage drop across the series resistance, and resistance is constant, so we have to adjust the series current ISE for maintaining the output voltage constant. So ISE, that is a deciding factor for maintaining the output voltage constant. Now ISE, as we have seen, that it is IL plus IZ. So we are controlling the Zener current to maintain the ISE as per our requirement. So as per definition of working, Zener diode adjusts its current such that its voltage remain constant irrespective of the changes in the input voltage or in the load current. So with these two equations, we can easily understand that to maintain the output voltage constant, the important point is the voltage drop across the series resistance, and for that the value of series current, total current ISE, that is very important, and that is maintained with the help of Zener current. So VI, that is equal to VO plus IL plus IZ, that is total ISE current. We have substituted the value of ISE and multiplied by RSE. Now let us see the first case. Load current is constant and input voltage increase. In this condition, Zener current increase, and so total current from the series resistance, that is ISE, also increase, and then as a result voltage drop, that is a ISE multiplied by RSE, the voltage drop increase. So the increment in the input voltage is compensated with the increase in the voltage drop across the series resistance. So VI, that is equal to VO plus voltage drop across the series resistance. VI increase, in case number 1, VI is increasing. So to maintain the output voltage constant, this product, that is voltage drop across the series resistance, must increase. So increment in input voltage VI is compensated with the same amount of increment in voltage drop across the series resistance. And this is done by increasing the Zener current in such a way that sufficient amount of ISC, that is series current, increase. Case number 2, load current is again constant, but input voltage decrease. Now in this case, IZ, that is Zener current, decrease. Then current through the series resistance, ISC, that also decrease, and voltage drop across the series resistance decrease. So the decrement in the input voltage is compensated with the same amount of decrement across the voltage drop in series resistance. With this mathematical equation, we can understand that if VI, that is input voltage, if decreasing, then same voltage drop across the series resistance must decrease, and that is adjusted by the Zener current. Such amount of Zener current decrease in such a way that sufficient amount of ISC also decrease. Now case number 3, load current increases, input voltage constant. In this case, if load current increase, total current ISC also increase, and voltage drop across the resistance must increase and output voltage decrease. But to maintain the output voltage constant, now Zener current decrease. So the same amount of increment in the load current, accordingly same amount of Zener current decrease to maintain total current ISC constant and to maintain voltage drop across the series resistance, that is ISC multiplied by RSC, constant. So there is no any effect should be reflected at the output voltage, and output voltage is maintained constant. We know that total current ISC, that is IL, that is load current, plus IZ, that is Zener current. Now in this case, load current IL is increasing, so IZ must decrease in such a way to maintain the total current ISC constant. Now case number 4, load current decreases and input voltage is constant. In this case, IZ, that is Zener current, increase to maintain the total current ISC constant, and so voltage drop across the resistance RSC remain constant. So with this equation, we can see that if load current is decreasing, to maintain the total current constant, IZ must increase. So this is how the application of Zener diode as a voltage regulator, how Zener diode is applicable to maintain the output voltage constant across the load. Thank you for watching my video. Keep watching. Thank you very much.